This construction provides an illustration, a graphic illustration, of the concepts of limits and the derivative or slope of a function at a point. It shows a function in green with a movable point A along the x-axis, and a second point on the function to find a distance h away from A, where of course h can be changed by moving the slider here. These 2 points on the function determine a line, and the slope of the line is given by f of a plus h minus f of a over h, which in this case is equal to 0.45. As I let h approach 0, the slope of this finite approximation to the derivative approaches the slope of the tangent. When h is exactly equal to 0, although this function is undefined, its limit becomes the slope of the tangent line, which in this case is 0.93. So as I let h increase, we can see how the actual derivative, or the tangent line, varies from the finite approximation. So when the curve is very steep, they're pretty close together. As we go into this down steep portion of the curve, we reach a point where they're exactly equal, and then they spread apart again as they move further up to the right. If h is negative, I'm looking at 2 points, a point below h, A, and a point at A, to determine the slope. The smaller I make the value of h, the closer the 2 points are together, the better the approximation of the finite slope line to the actual tangent. So as I move this, you can see that the 2 lines stick pretty much together. So this shows the value for a cubic function shown here. A more interesting function is given here, where f of x is equal to the absolute value of x squared minus 1. In other words, the lower point of the portion of the parabola below 0 is reflected upward, and so we reach a place where 2 points where, although the function itself is continuous, the slope is discontinuous at the point x equals minus 1 and x equals plus 1. So let's watch what happens as I move the value of a into them. As you see, when I hit a to be exactly equal to 1, which is at one of the breakpoints in the slope, the tangent slope becomes undefined, but the finite approximation remains valid. So as I move a down, we can see that for h greater than 1, I have a slightly positive slope. When h becomes just less than 1, there is an abrupt jump in the slope of even the finite approximation. So let's watch what happens as I move through this. So that again, let me move so that they're slightly different. So let me move the point A through the discontinuity in slope. And what you see is the finite approximation gradually changes from positive to negative, whereas the tangent line itself makes an abrupt jump. So this is an example where the function itself is continuous, but the slope is discontinuous at these 2 points.